morning, Townview. Welcome back to Chemistry Online.
So what is polarity? Polarity is basically when you have a positive side and a negative side. So let's start by talking about the Earth. So the Earth has a northern side and a southern side. That's the North Pole and the South Pole. Because of that, we have the electromagnetic field, which enables compasses to always point north. So that's what polarity means. It basically means that we have a positive side and a negative side. With regard to chemistry, what does that mean? It means we basically have let me give you all an example. So here's HCl, hydrochloric acid. So the hydrogen is going to be our positive side. The chlorine is going to be our negative side. Things that don't have polarity are going to be things like O2. So O2 is a very simple example. Both of these oxygens have the exact same pull on their electrons, which means there's not a side that's more negative or positive than the other side. So in this scenario, this is going to be nonpolar. So here is nonpolar. Over here we have something that's polar because we have a positive side and a negative side. So let's go ahead and discuss. So polar covalent bonds. We only discuss polarity when we're talking about covalent bonds because when we're talking about ionic, something like lithium chloride, we know that lithium is always going to have a positive charge. We know that chlorine is always going to have a negative charge. And we call this ionic. So we don't talk about polarity when we're talking about ionic things. Polarity is only involved with covalent bonds. What are covalent bonds? Covalent bonds is when you have a nonmetal bonded with another nonmetal. So examples are going to be something like SO2. So sulfur dioxide, we have sulfurs and oxygens, which are both negative and positive. However, because oxygen in this scenario is going to be more negative, it's more electronegative. It's going to act as our negative side, where sulfur, even though it's negative, will act as our positive side. So we'll discuss this more in a little bit. But basically, what is a polar covalent bond? It's when electrons are not shared equally. So one thing is hogging the electrons. So if we look at something like HCl, or let's do HF, because fluorine is the most electronegative element. You guys know that. So hydrofluoric acid, the electron that fluorine takes away from the hydrogen is going to be very close to the fluorine. That's because fluorine is electronegative. It's going to hog those electrons. So fluorine in this scenario is going to be our negative side, and then hydrogen will be our positive side. So that's really what polarity is. Now, the types of questions you're going to see, you saw one on the last test we took, which of these molecules is going to be polar. So what you guys need to be able to do is determine whether a molecule is polar or nonpolar. So let's go ahead and work on that. So before we talk about polar, we're going to do nonpolar first. So nonpolar is pretty easy to identify. So on your page, I want you to write out nonpolar. Did y'all know in Spanish the question mark is written backwards? Shh. All right, so for nonpolar, first thing that's going to be nonpolar is first thing that's going to be nonpolar is a monoatomic atom. Can anyone tell me what monoatomic means? All right, so that's going to be one atom elements. Examples of these are going to be helium, neon, and argon. So these things have no desire to bond to anything. So if you had a tank of helium, all your helium atoms are going to be on their own. They don't do what oxygen does and form a double bond with another one. They don't do what hydrogen does and just bond with another one. They don't do what fluorine does and just bond with another one. So these are all monoatomic, and none of these are polar because it's just a single atom. We don't have a polar side or a nonpolar side. Next thing that's also nonpolar is going to be diatomic. Why are diatomic elements nonpolar? Anybody want to guess? It's because they always share the same electronegativity. So oxygen has an electronegativity about 3.0. This oxygen has an electronegativity of 3.0. So basically they both have the exact same pull on their electrons. So this is equal sharing of electrons, which means O2 and N2 and Cl2 are all going to be nonpolar molecules. So the first category of nonpolar is going to be the monoatomic and the diatomic. Both of those are going to be nonpolar. Our next category is going to be hydrocarbons. Hydrocarbons are exactly what they sound like. They're molecules that are made of only carbon and hydrogen. So CH4 is an example, C2H6, C2H4. All of these are examples of hydrocarbons. Now, hydrocarbons will always be nonpolar. And hydrocarbons, they only have carbon and hydrogen. I'll show you all some examples later, which include some hydrocarbons. However, when I say hydrocarbon, I'm talking only carbon and hydrogen, nothing else involved in the bond. Last one, which is the most difficult for people to answer, is going to be symmetrical molecules are nonpolar. Now, what is a symmetrical molecule? Let me go ahead and draw one out for you. So CF4, carbon, and it's going to have 4 bonds. It's going to be bonded to fluorine. And I just want to draw this right. So carbon has 4 electrons, and then fluorine has 7, 14, 21, 28 electrons. So we should have a total of 32 electrons. We just used 8, so we have a total of 24 left. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, and 24. So that's our final product right there. What kind of charge is going to be on the fluorine? It's going to have a -1 charge. This one has a -1 charge. This one has a -1 charge. And this one has a -1 charge. Now, let me grab this molecule. Here's what a CH4 looks like. You guys made them last week. Here's what a CH4 looks like. Does it have a positive side? No. What are all the sides? All the sides are negative. So it's not polar. It's basically symmetrical. And any way we cut this thing, all we have are negatives on both sides. So because it's negative on both sides, this would be considered a symmetrical molecule, and that's going to be nonpolar. Next example is going to be sulfur hexabromide. That's going to be a sulfur in the middle. I don't want y'all to worry too much about this example. You're not going to see examples like this one. But then you're going to have bromines on each side. I'm not going to draw all the electrons, but what's the charge on all the bromines going to be? They're all going to be negatively charged. And for that reason, this is another example of symmetrical. And symmetrical things are nonpolar. All right, next one is CO2. Carbon is going to be our central atom, single bonded to 2 oxygens. And I want to draw this one right. So we got 4 plus 12. That's going to be 16 electrons. We just used 4, so we have 12 left. So 2, 4, 6, 8, 10, 12. And then these are going to go away to create a double bond. These go away to create a double bond. All right, so when we look at this one, what's the charge on the oxygens going to be? What do y'all think? All right, they're each going to have a minus charge. So do we have a positive charge here? No. This is another example of nonpolar symmetrical. Last example is going to be BH3. That's when we have a boron in the center, and it's going to be bonded to 3 hydrogens. Our hydrogens are all going to be positively charged. Is this one going to be polar? No. Also symmetrical, also nonpolar. So a lot of times students will look at this one and want to call it non-symmetrical. But that's not really what I want y'all to look at, not the symmetry. I want you to look at the charges. So the only parts of this molecule that are exposed are the positive parts. And for that reason, this would be a nonpolar molecule. It's only got a positive side. It does not have a negative side. Any questions on nonpolar? All right, let's keep moving. So next up, we have how do we identify a polar molecule? So one easy way to identify a polar molecule is if it has hydrogen bonding. What is hydrogen bonding? Hydrogen bonding is when you have a hydrogen that's bonded to nitrogen, oxygen, or fluorine. So if you have something like CH4, this does not have hydrogen bonding. But if you have something like H2O, this one does have hydrogen bonding because you have a hydrogen that's bonded to oxygen. So over here we have our example HN. So this is going to be polar. NH3. So NH3 for multiple reasons is polar, but let's go over the most important one. So you have a nitrogen that's bonded to 3 hydrogens, and then it's also got a lone pair. What shape is NH3 going to be? It's going to be pyramidal. Good. So here's another really important thing to write down. So anytime you have a lone pair on the central atom, you're looking at something that's polar. So this lone pair is going to make the nitrogen what? It's going to make it negative, and then all of our hydrogens are going to be positively charged. So now we have a negative side and a positive side. And something that the hydrogens do is they all pull towards the other side. So ultimately, this is what our shape is going to look like. All right, next one is HF. So hydrofluoric acid, fluorine is minus, hydrogen is plus. CH3OH, I'll draw this one over here. So this one, it's got a hydrocarbon in it. So it's got CH3. And then the carbon is bonded to an oxygen that's bonded to a hydrogen. So here you have your hydrogen bond. But another thing you have is the symmetry, or the lack of symmetry. So we have lone pairs here, again, on one of the atoms. And for this reason, this oxygen is going to be negatively charged. And then all these hydrogens are going to sort of lean the other way. So they're going to come out this way. And they're going to have that positive charge that's necessary to make a polar molecule. I'm not going to draw this one, but it's the same idea. So just replace the oxygen with a nitrogen and throw in another hydrogen, and you got yourself that example. All right, let's keep going. So on the last slide, we had CO2, and CO2 looked like this. It was a carbon that was double bonded to 2 oxygens with 2 lone pairs on each of the oxygens. Over here, we have COS. So in COS, you have a carbon in the center. It's bonded to an oxygen, and it's bonded to a sulfur. Now I want to do this one right. So we got 4, 6, and 6. So we have a total of 16 electrons. We just used 4, so we have 12 left. 2, 4, 6, 8, 10, and 12. And then to fill the octet, it's going to take 2 electrons from there. And to fill this octet, it's going to take 2 electrons from there. Now, COS is different from CO2. Even though they look the same, is this one symmetrical? No. What's more electronegative, oxygen or sulfur? Oxygen is more electronegative, so oxygen is going to be our negative side, and sulfur is going to act like our positive side. So even though sulfur is not positively charged, compared to an oxygen, it is. It's more positive than an oxygen. So in this scenario, it's going to be our positively charged side. All right, let's keep going. Another reason is this is just not symmetrical. You can see we have sulfur on one side, oxygen on the other side. So next up, we have CH3F. So we got H, H, and H. And then here we got our fluorine. Our fluorine is going to be negative. Our hydrogens are going to be positive. Another example of non-symmetrical. So any way you cut this, you have a negative charge on one side that doesn't exist on the other side. Last one we have is SO2. So sulfur is going to be in the center, single bonded to 2 oxygens. And let's count this up. So that's going to be 18 electrons minus 4. So 14 left. 2, 4, 6, 8, 10, 12, 14. Now to get an octet, it's just going to break one of these bonds and double bond to this one. And now we have our Lewis structure. So what shape is this one going to make? Is this going to be linear? It's not tetrahedral. For tetrahedral, you need one thing bonded to 3 things. All right. Bent is correct. But for tetrahedral, it's one thing bonded to 4. That was my bad. So it's going to be bent. Here's sort of what it's going to look like. So you have a double bond on one side and then a single bond on the other side. What makes it bent? It's got a lone pair on the central atom. Now, we already mentioned that lone pairs on the center will make it polar. So there are 2 shapes that always have a lone pair on the central atom. What are they? Bent is one. What's the other one? Pyramidal. Good. So pyramidal and bent are always going to be polar. They're always going to be polar. For tetrahedral, this one is tetrahedral. It can go either way. Sometimes it's polar, sometimes it's nonpolar. Linear, same thing. Sometimes it's polar, sometimes it's nonpolar. Triagonal planar, also sometimes polar, sometimes nonpolar. However, bent and pyramidal are always polar. All right, any questions on polarity? Let's go ahead and take a look at more examples. So here we have CCl4. You can see that it's symmetrical. This is nonpolar. Over here, CO2, nonpolar. And then here, even though we have chlorines that have a negative charge and our hydrogens have a positive charge, these are going to cancel each other out. And this would be considered nonpolar. So it's symmetrical and it's nonpolar. All right, let's keep going. So here we have our polar molecules. So OF2. And here we just have two versions of it. So this is the same as this, except here you can see the geometry. And our fluorines are going to be our partial negatives. And then our oxygen here acts as our partial positive. Here we have our H2O. You can see that the central atom has lone pairs, just like it did up here. Anytime central atom has lone pairs, you're looking at something that's polar. And then here, our last example, this is just non-symmetry. So you have a triple bond with the nitrogen, single bond to hydrogen. And because of the lack of symmetry, this is going to be considered polar molecule. Nitrogen is negative, hydrogen is positive. All right, do we feel good about this? All right, let's go ahead and do some examples. I'm going to give you guys 4 minutes to work these out. So you can draw them or not draw them. I recommend you draw them. That way you know them a little bit better. And then we'll go over them. All right, so the first one, what shape is this? All right, bent is correct. So polar or nonpolar? Polar. Let's go ahead and solve it real quick. So we got sulfur, and then you're going to have chlorines on the outside. And these are each going to have an octet. And then we're going to have 2 electrons on, or 2 lone pairs on the sulfur. And because we have lone pairs on the central atom, this one's going to be polar. Let's go ahead and look at the next one. So what shape is CH4? All right, this one's going to be tetrahedral, polar or nonpolar? Nonpolar. Next one is CO2. What's the shape? All right, linear is correct. So it's going to be carbon that's double bonded to 2 oxygens. You've seen me draw this probably 100 times today. And then polar or nonpolar? Nonpolar. And then NH3, what's the shape? All right, so pyramidal. For pyramidal, you're going to have a nitrogen, and it's going to be bonded to 3 hydrogens. And then how many lone pairs? All right, just 1 lone pair. And is this polar or nonpolar? Polar. And then our last example is going to be boron attached to 3 chlorines. What shape? Triagonal planar. And then polar or nonpolar? Nonpolar. So I'm not going to draw all the electrons here, but this is correct. So this is planar, triagonal planar, and it's nonpolar. Because anytime you have a lone pair on the central atom, the lone pair makes the central atom negatively charged, and then all these hydrogens are positively charged. So lone pairs on the central atom, just keep that in mind, will always be polar. All right, so I'm going to go ahead and end this video right here.
If you don't know how to do chemistry, hit that subscribe button. Let's